Hi everyone, and welcome to the System Design Path. On this channel we do deep dives on various system design topics, and today we are going to talk about Uber's system design. First, we'll cover the three main system design concepts that we'll be using in our Uber design. Then we'll discuss the high-level system design, drill down into the multiple components, and go through the main workflows. Finally, we'll discuss the performance improvements as well as the trade-offs between using the GeoHash and the QuadTree. When we consider Uber system design, we want to make sure that we cover three main system design concepts. The first one is proximity service, or how we work with maps. When we try to book a trip, we want to be able to give the key closest drivers to us and send them requests for the ride. The second concept is how riders and drivers connect to the backend system. In our case, everyone has to be connected to the server in a bidirectional manner. Every single time the driver moves, we want to be able to send the driver's location to a server and then to a rider. At the same time, when the rider books a trip and moves left or right, we want to update the drivers and tell them where the rider is. The bidirectional connection will be represented as a WebSocket. However, managing millions of WebSocket connections that have to be persistently stored somewhere on the server is not easy. This design is very similar to the messaging system where we had one-to-one and group messaging. All the people had to be connected to the messaging servers to see the updates. I talk a lot about the WebSocket system design in my video on designing a messenger like WhatsApp. If you want to learn more how to manage the WebSocket connections and the routing to different clients, check out my video on the messaging application. The third concept of our system design would be a generic architecture, where outside of covering the proximity service and the website connectivity, we would talk about the domain design, the database design, how the driver and rider would match, how the trip would be created, and how we would store it, etc. And this is what we are going to talk about today. We're going to cover the main components of the Uber system and the main workflows. Let's start with the proximity service. In our case, the design is going to be a little different from the regular static Yelp-like proximity service, because Yelp has static objects on the map, and for us to be able to retrieve them, it's a relatively simple task because it's all read-only operation. Those objects are not moving between the segments or nodes in a QuadTree. They are static and rarely updated. But in the case of the Uber, drivers represent static entities that used to be restaurants when we designed Yelp. Drivers are moving, so their location gets constantly updated. And since they are moving, we need to move those entities between different segments as they change location. This is not a trivial task, especially when we have millions of drivers and our GeoHash or QuadTree has to be read from and updated very frequently. Okay, this covers the thought process of how we would go about the Uber system design and its components. Now let's talk about the high-level system design and the main workflows. From the very high level, this is how our system would work. We would have two flows, a rider flow and a driver flow. So let's go from upside down. We have a rider who opens up an application. Rider sees a list of different types of rides available for the specific destination. Then we click Request. While we wait, the system is looking for the driver, and we can either get matched with the driver or receive no cars found. If we get matched, we receive the trip information. It means that the trip is created on the backend. Now it's the main entity that will be updated throughout the trip lifecycle. From the driver perspective, let's say I'm a driver and I don't have any passengers. I send my application to the application every, let's say, 5 or 10 seconds. So the application can track my movements and match me with the rider closest to me. Then I receive a ride request and either accept or decline it. If I accept it, a trip will be created on the backend and sent to the rider. Now the rider and the driver share the same trip object stored on the backend. This trip will be updated in the backend as it starts and eventually completed. Now let's go one level deeper. As you can see on this diagram, we have more components here. As we've discussed in the beginning, the rider opens up the application and we first show the closest drivers to the rider. For that, we would need to use our location service and give the closest key drivers to the rider. Now, as the rider enters the destination, he can see a list of different rides available for him based on the vehicle type and other factors. The next step is for the rider to choose the trip type and click Request. This is when the request goes to one of the closest drivers. The first rider who accepts the trip is matched to the rider and the trip is created. Drivers constantly send their location and status to the location manager. The status is whether they are currently free or have passengers, and the car's location. The location gets updated in our map representation, which would be either the GeoHash or QuadTree. It would be used to retrieve the closest drivers to the specific location. The driver matching service is the key because it connects the rider flow and the driver flow. When a rider sends a request for a ride, it queries the location manager database for the key closest drivers and then tries to match them with the rider. When a rider sends a request for a ride, it queries the location manager database for the closest key drivers and then tries to match them to the rider. When the match is done, the trip gets started and eventually gets completed. When the trip is created and the rider or driver cancels it, the trip ends and the rider goes back to looking for drivers and the driver goes back to driving and waiting for the rider request. Now let's extend our diagram and add more components. As you can see, we still have two main workflows, but now you can see three different components that connect our main workflow of the rider and driver. We have a driver matching service that connects and matches the rider with the driver, creates a trip, and updates the trip until it's marked as completed or canceled. In more details, the rider is connected to our system through the load balancers and WebSockets. This part of the system misses components like the WebSocket routing service, Redis database, and the whole routing of WebSocket infrastructure, which, as I mentioned, I cover in my separate video on the messaging application, so I'm gonna skip it for now. All we know is that the rider and the driver connected to our system using WebSockets. They have a bidirectional connection, which means that they can send the location information to the server and then receive updates from the server about the location of either the driver or a rider. Let's start with the rider flow. As the rider opens an application, the first thing we see is all the cars around us. So the vehicle finder service queries the location manager and retrieves a list of cars closest to where we are. Once we type the destination, the vehicle finder groups all the drivers by the vehicle type and computes an ETA for every driver. Now in our application, we can see every type of the trip available with an ETA on it. At the same time, if you're a driver and you don't have any passengers, you send your location through the WebSocket to a location manager that updates your location in the GeoHash map service. Then every single rider who asks for a ride in the area will see you as an available driver. Now let's say the rider sends a request and drivers receive a notification about the possible trip. So here, if we have multiple cars, we can have a different service like reputation service, for instance, for the drivers, where we first send requests to the drivers with the highest reputation or some premium accounts, for instance. If none of them accepts the trip, let's say in 5 or 10 seconds, we send the same request to the second tier of drivers and the third tier, and then keep sending the request to more and more drivers to be able to match as soon as possible. Once the trip is matched, the trip object is created, marking this request as completed. If any other driver presses accept after that, the request comes to the database and gets rejected because there isn't already a trip object assigned to this request ID. Now, the biggest challenge with this design is the ability to maintain real-time information about the location of the drivers. The location manager is responsible for returning the closest K drivers to the rider. This query is the most important, and we need to serve it as accurately as possible. As drivers keep moving, their location changes constantly. So not only do we need to serve a lot of queries from the location manager for every single rider request, but we also need to write a lot to our database to update the driver's location in real time. There are multiple options we can implement. First, we need to choose between using a GeoHash or the QuadTree. In our case, since we have so many frequent updates, it would be incredibly hard to maintain a QuadTree. I'll explain why. A QuadTree is an actual tree. It has good search performance, but if we try to update it at the same time, then we would need to change the structure of the tree. And to do that without sacrificing consistency of our reads, we would need to implement locking, which would reduce the performance dramatically. The second problem is that the tree is in the memory. It's not a database, and we can't afford to have a QuadTree down because it always has to stay up for the system to work properly. So we would need to implement a persistence layer. So now we are talking about a full custom solution that acts as a QuadTree with the persistent layers and backups. The complexity grows enormously. The simpler option is to use GeoHash because it's a hash-based algorithm, and the updates would be so much lighter because most of them would not require any locking mechanisms. We can read and update hash map or hash table in real time. We might still get stale data, but we can tolerate it. GeoHash would be easier to implement and to use. The next question is how often we send updates from the driver and how often we update the driver location in our GeoHash. We can do it every 30 seconds or every minute. The best approach here is to send data from the drivers every 30 seconds, cache the driver location in Redis, and then update our GeoHash every 30 seconds. This way we reduce the load on our GeoHash map service because it's only used for a single use case, receiving the top K closest object to the user. All the updates for the driver locations will come from the close to real-time Redis cache. Okay, at this point we've covered the main workflows and components of the Uber system design. If you found this video useful, make sure you like and subscribe, and I'll see you in the next one. Bye.